Welcome to all Quaternions. First, we're each going to talk about what we did for Project 6, and then you're going to see the special surprise at the end, which is our final render for Project 7.
As you can see, we have general textures, and if I enable, this is normal mapping, so we have regular normal maps, and then in particular, we also have height mapping or bump mapping, and also parallax mapping. So as you can see, the windows are actually like set in, and there's this illusion of displacement. The same is on the ground. This is like with bump mapping and parallax mapping, and this is just the plain texture. This is again bump mapping, parallax, and then normal mapping only.
What I implemented for Project 6 was rigid body translation and rotation to get the physics working for our eventual final render. And here in the background, you can see just basic examples of force and torque being applied to rigid bodies, getting them to accelerate both linearly and angularly. And we even have torque that can be applied on multiple axes and non-uniform inertia, so you can see that cone wobbles. For Project 7, I implemented collisions, and you can see how everything bounces on the floor there. And this is what our final project looks like without any of the extra bells and whistles, just the physics.
Next, we have particle systems, where separate fragment and vertex shaders are used to color hundreds of thousands of tiny 2D particles that are always oriented to face the camera to create 3D effects. Here's an example of a pile of fire particles, but the parameters could be easily changed to create other effects, like a big fire, small fire, tall fire, short fire, wide fire, narrow fire, blue fire, green fire, or even no fire. You get the point. Lastly, we have camera paths, where the position and the yaw, pitch, and roll of the camera are defined at certain points and interpolated linearly using Bezier curves. Here, we have a pretty basic circular camera path, but by adjusting some input parameters, we can create funnier camera paths, like a spiral one or a zigzag one.
And what you've all been waiting for.
Hey everyone, my name is Garv and I worked with Alex and Phila on our project called AstroView. Now what you're seeing on the screen is our GPU ray tracer for black holes, and that involved a few steps. Particularly to create these images with the black hole, we had to implement a ray marcher with sphere tracing on the GPU, which involved processing rays in parallel. Additionally, we used SDFs instead of VBOs because they allow us to more exactly render shapes and trace light paths using ray marching. Now, the way we get the curvature is by using something called geodesic ray tracing, which essentially involves computing curved paths of light rays that are distorted by the black hole. And geodesic basically describes the shortest time path that light can take in a gravitational field. So we apply some general relativity corrections to get the actual path of a black hole. Additionally, we implemented texture mapping and fractals on the GPU. So as you can see here, this is the Julia set with and without the black hole. This doesn't exactly have infinite resolution because ray marchers stop within some threshold of the SDF. This is the Mandelbulb with the black hole around it, and you can see there's some pretty cool lighting effects. Additionally, we applied HDR rendering so we could get clearer images and better tone mapping. And so to support physically plausible lighting, we use high dynamic range rendering. We combine ambient, diffuse, and specular terms using full floating point color values and put it in a floating point frame buffer to avoid color clipping. And then in post-processing, we apply tone mapping. What you see here is a generated terrain that goes on infinitely, and you can see these hills are artificial and are particularly generated or particularly emerge when you have a black hole near the terrain. This is a sphere with a torus around it, and you can see there's some pretty cool effects, especially when you realize that the circle around the torus is supposed to be simply circular. Additionally, we showed this one before, but this is like an inverse of the Mender sponge that we computed for a few iterations and more fractal geometries because we think these are pretty cool to see. Another feature I mentioned before is called sphere tracing, and essentially what that describes is optimizing the amount we step by using the distance to the nearest shape. because the sign distance function gives you a distance in object space, which you can then convert to world space and use that as an optimal step size in Euclidean geometry, and applying some corrections in curved space, like in the vicinity of black holes, you're able to ray trace or ray march much faster than you would be if you took just discrete time steps. Thank you guys so much for watching our presentation, and I hope you guys enjoyed.
For this project, we implemented a procedural crystal cave geometry generator, combining a Perlin noise-driven height field cave shell with stochastic instancing of crystals and pillars. The shell is built on a regular grid, controlled by parameters that adjust the tessellation level and overall scale while preserving the overall tunnel shape, which uses layered Perlin noise to make the shell more jagged and cave-like. Crystals were implemented as parametric polyhedra instanced stochastically along the tunnel. Randomized height, radius, tilt, and twist together with shared segment counts control how faceted they appear. Rock pillars were then constructed from stacked rings that interpolate in radius from the floor to the ceiling with additional jitters, so even the supporting structures feel irregular and organic. A few simple parameters control how many crystals and pillars are created and how detailed they are, which makes it easy to dial the scene from sparse to very dense. Altogether, these give us a flexible procedural cave that we can reuse across many different parameter settings.
For the core pipeline, spectral path tracing was integrated as the core renderer. Switching from ray tracing to path tracing lets us have global illumination, allowing us to make the spectral phenomena more visually striking. By using spectral rendering, we can model unique effects by changing the way we represent light. Instead of the typical R, G, and B values, we represent rays of the entire spectrum of light. This allows us to model effects such as diffraction, in which we split up light as it hits a surface based off of its index of refraction. With this, we can see bouncing rainbows in our materials, as well as the caustics projected onto surrounding surfaces. Or we can model effects such as fluorescence, in which a material converts invisible wavelengths of light into visible wavelengths, giving us the visual look of a material glowing, while still conserving energy across the spectrum. Or we can do both and see how these unique effects play on one another.
My part of the project was implementing area lights. With area lights, the light is represented as a surface, and soft shadows are produced by sampling multiple random points on that surface. The ratio of unincluded to total shadow ray determines the softness of a shadow. Compared to emissive spheres, area spherical lights give more uniform lighting throughout the scene, especially at lower sample counts. The trade-off is that we only sample them for primary rays or rays from the camera. Indirect rays and spectral rendering don't sample them for performance reasons. We can combine these two together when area lights can be used to brighten the scene, while emissive spheres are used to create more of the effects for spectral rendering.
To render non-solid objects like smoke or fog, we use ray marching within the region of the volume, sampling the densities at given points in the interval. Once we accumulate these densities, we calculate the transmission of light using the Beer-Lambert law. Once we can find the regions where light is being obscured, we replace where light should have been with our chosen color. We create our own noise algorithms for Perlin noise and Worley noise to create these cool patterns for volumetrics, as well as blending them together with different octaves and creating these nice little cloud patterns. Overall, the result is where we can create this beautiful cave scene combining all the features that we've done, as you'll see right now.
Hi everyone, we're Danimal Glossing. I'm Yali.
I'm Sue-Ann.
I'm Max.
And I'm Seyoung.
Here's a quick look at our final scene. We're going to now go into the scene and show you all the different intricacies and parts that make it up.
First, we use color grading to apply a filter to our entire scene to add a more Animal Crossing style. Next, we can see the stylized filter that is applied to show a line art style filter applied to our objects. We also implemented bump mapping to make the textures for our floors look a bit more bumpy and realistic. And scrolling texture helps us to animate the water and make it flow like an ocean. Next, we also have depth of field, which allows us to adjust the focus plane where we can blur the objects that are far away from us and focus on the ones that are near us.
For the daylight scene, we use directional lights, so here we can see harder shadows, but in the nighttime scene, we use point lights, so you can see softer shadows there. And here you can see the cat shadow as well. And we use particle systems to snow. And this is another stylized filter where we do pixelation, and we can change the pixel size to give a more retro style.
This is a nighttime version of our scene that we're showcasing using camera paths implemented with Bezier curves. This is without the pixel stylized filter applied. Now we'd like to show some objects in our scene that we imported using an OBJ file loader.
Now we're going to showcase our depth of field. Here we see we're coming up close and focusing on Isabel. Now with our pixel filter turned on, we can see that the pixels still apply even with the depth of field effect. We do this by having a pixel pass within the depth of field pass. We're going to move over right by Tom Nook now and show you the scene from behind. In this scene, we have 8 lights, 1 from the moon, 6 lamps, and 1 from the fire. This is very computationally expensive for shadow mapping, but we think it shows a really nice effect. Thank you for watching.
For the trees and shrubs, we use L systems to generate randomized tree variants. We imported OBJ objects as the shapes to be used for drawing the branches and leaves. To have more variety within our trees though, we use different rules to generate different types of trees,
gave each tree a randomized scale and randomized the rotation of each branch. To start off post-processing, we added a stylized filter, specifically a Kuwahara filter, to give the scene a painterly look. We also added a sky dome with a night sky to add to the ambiance of the scene.
HDR rendering gives us the option to render higher intensity light values. This allows the bloom in our scene to shine even brighter. It also gives us an option to adjust the exposure of the scene to reveal more of the background. The screen space bloom was applied to the fire particles in order to make the lighting more realistic. It essentially takes the brightest pixels in the scene and blurs them separately before re-adding them on top of the existing pixels. The color grading was used to give a different vibe to our existing scene. We used a lookup table of cooler toned values to create a bluer visual than our originally warmer toned scene.
The scene also contains fog that could be placed at different distances. Any pixel behind the maximum distance is completely fogged, and any pixel in front of the minimum distance is completely clear. In between the distances, there is a varying amount of fog.
To create the campfire, we instanced over 1,000 particles to model fire dynamics such as heat transfer and decay through different collisions. During a collision, heat is added to a particle, which changes the color from black to red to orange. In addition, once a particle's heat reaches a certain threshold, an upward force is applied, which then varies the shape of the rest of the flame. We also coded different camera paths for this demo, as well as billboarding, which makes sure that the fire plane is always facing the camera.
We created a 3D world using procedural generation, used a post-processing shader to achieve a certain visual effect, and implemented rigid body physics to enable a car to drive about the world. We used the wave function collapse algorithm to generate an initial 2D bitmap. This variant of wave function collapse takes in a set of tiles and constraints that define which tiles can share an edge with which other tiles. It generates a 2D grid of the tiles that satisfies the edge constraints using the following procedure. Each tile slot begins by having the possibility of becoming any of the tiles. A tile is randomly selected, and a concrete tile is chosen for it randomly. We then restrict the set of tiles each of that tile's neighbors can be according to the edge constraints, and then propagate this outward. We repeat this procedure by selecting the tile with the lowest number of possibilities to collapse next, iterating until all of the tile slots have concrete tiles. To turn this into a 3D world, we use simple heuristics to generate height maps. We collect all of the edges of our islands and then start a breadth-first search inward from each of them, performing a random walk to determine the bottom and top Y levels at each XY coordinate. The random walks are weighted to ensure that the bottom of islands is further down the further you are from the edge, while the top stays roughly the same. With our bitmap and height maps, we generate colored voxels to create our world. To make the world more visually interesting, we also apply a post-processing shader that uses Sabel filters to emphasize edges.
For the rigid body physics, we generate the entire world using just cubes. There are two parts to the player movement mechanics, the linear motion and the angular motion. The keys W and S adjust the linear motion by applying a force to the cube, either in the forwards or backwards direction. Neither of these keys apply angular motion. For rotation, we use the A and D keys, and rotation is implemented via Quaternions. When we click these keys, we apply a torque to the player that causes the player to rotate. We also implemented friction for both the linear and angular components. This simulates driving and makes the car stop moving if you're not putting your foot on the gas using the W and S keys. So, to recap, for each tick, we calculate linear motion using the force applied from the keys and the friction force, and then we calculate angular motion using the inverse inertia matrix, the inertia, Quaternions, and torque, which get updated constantly. To handle the collisions between objects, we create bounding boxes around all the cubes, and then see which environment cube our player intersects with the most. And once we calculate that, we move in the opposite direction depending on how fast we are going at that time. The mass of all the environment cubes is infinite, so they never move. Finally, our camera tracks the movement of the player by always updating the camera's view projection whenever the cube moves.
Hi, I'm Jason Liu.
And I'm Veronica Gritzai.
Our project is called Ginkgo. The geometry generation of the project consists of a space colonizing Venetian algorithm based on Runians et al., which is accelerated by a KD tree. We grow the graph by repeatedly adding new nodes based on their proximity to randomly placed target positions called auxins. For each edge on the graph, we create a cylinder along it. After testing linear and power scaling, we use a flood fill method and apply logarithmic scaling based on the flow over each node. In this way, newly added edges are progressively thinner. By changing the placement of auxins, we can get different branching patterns. If we place them a distance above the starter nodes, the tree will grow straight up before branching out.
Each shape is given a nice voodoo texture using bump mapping. We use bump maps that showcase high difference to calculate new normals for each pixel, which we later use during lighting.
We additionally explored Bezier surface tessellation. At first, we replace each cylinder with a Bezier surface tube whose control vertices are perturbed to create a more organic look. Then, we computed the maximal degree 2 paths over the graph and also the frame along these polyline curves, so that we can make a single surface spanning multiple edges. Turning up the meshing resolution creates a smoother transition over edges connected at an angle.
This scene demonstrates advanced ray tracing with multiple overlapping distance estimated fractals rendered with noise textures and bump mapping. You see a Juliet-Sack cathedral combined with Mandelbrot structures, all rendered through ray marching with depth of field and image-based lighting, using a cave environment map. The central cathedral uses a Juliet-Sack with Quaternion constants iterated 20 times. Additional Mandelbrot fractals with power 16 and 15 iterations create cave-like overlays, rate marching steps along the ray, evaluating distance estimators at each point until hitting a surface. Each fractal uses a unique distance estimator function. The Juliet-Sack squares quaternions, while Mandelbrot raise spherical coordinates to high powers, creating spiky organic geometry with infinite detail. Multiple point lights with physically based attenuation illuminate the scene. The cave environment map samples spherical coordinates, providing realistic ambient and specular reflections by treating the entire surrounding as an infinite light source, creating natural global illumination. Depth of field uses aperture sampling, 16 rays per pixel from random disk positions, all converging at a specified focal length. The overlapping distance field create complex intersections where mathematical structures interpenetrate, demonstrating the power of implicit surface rendering.
For our insects, we used ray marching with signed distance functions, demonstrating an alternative approach to traditional polygon-based rasterization. Instead of using vertex buffers, index buffers, or texture mapping, we represent our 3D model entirely through mathematical distance fields. Each component of the insect, body, legs, eyes, and antennae, defined by sphere SDFs combined through constructive, solid geometry operations. At the core of our system is a distance-aided ray marching algorithm that implements sphere tracing. We also built a complete depth buffer by tracking how far each ray travels before hitting the insect surface. As we march rays through the scene, we accumulate the distance traveled at each step. And when a ray finally intersects the insect, we record this total travel distance as the pixel's depth value.
Hi, we are the team Interstellar, and we are excited to show you our relativistic ray tracer, which is inspired by the wormhole from the movie Interstellar. A wormhole like the one in Interstellar is governed by general relativity. One way to think about it is as drilling a ball out of two separate three-dimensional spaces, and then connecting those spaces with a kind of tunnel, or more precisely, a cylinder with spherical ends. To make the transition from our usual universe into the wormhole smooth, light cannot just travel in straight lines anymore. Instead, light rays that pass close to the wormhole gets bent by its gravity. How much they bend is determined by an ordinary differential equation that comes directly from the wormhole's space-time geometry. To simulate this, we implemented a paper by Kip Thorne and the Interstellar Visual Effects team, which numerically traces light rays backwards from the camera through curved space-time. Our model is capable of adjusting the width of the mouth of the wormhole, the depth of the neck of the wormhole, and the gravity of the wormhole, which affects how much light is bent by it. To visualize, we placed our camera outside the wormhole and points the camera towards the center of it. We used two spherical skyboxes on both sides of the wormhole and chose textures for them. We then rendered the image by solving for the ODE pixel by pixel. To speed things up, we use an optimization described by Scott Manley. Instead of computing every ray independently, we pre-computed ray directions only along the equatorial plane of the wormhole. Then we rotate those rays around the axis connecting the camera to the center of the wormhole. Using this approach, we made our ray tracer about 1,000 times faster. This speedup also allowed us to add 3D primitives to the scene. We can render spheres and cubes on either side of the wormhole, and even send objects through the wormhole to the other side of the universe. As these objects pass near the wormhole, you can actually see how their shapes are getting distorted, which gives an intuitive sense of how the wormhole is bending light. We also implemented bump mapping to make the surfaces look more realistic. And now, it's time to see some results.
Hello. For our final project, we're inspired by the HDR Nerve dataset, specifically on the complex indoor scenes that have been rendered just for the beauty of the interior design aspect of it. But in this project, we're focusing purely on the computer graphics side, classic rasterization with explicit geometry, materials, and lights instead of the 3D reconstruction of the nerve. Our scene comes from a pre-made Blender file in the HDR Nerve dataset. We exported the base scene as an OBJ file, including vertex positions, normals, and UVs, along with all associated textures. We then used Tiny Object Loader to bring those triangles and textures into our OpenGL pipeline in a format a real-time renderer can consume. From there, we render the indoor scenes and add a few more features, including soft shadows, camera movements, textures, HDR, bloom, and bump maps. So with bloom, you can see that the lights are glowing in a more nice fashion around the actual light bulbs itself because of the Gaussian blur.
We also implemented shadow mapping / soft shadows. So to make the shadows first, we wanted to determine what each light in the scene is able to see, and then render the scene from each light's point of view to store a depth map. Then we render the scene normally and compare if each position is farther from the light than what the light recorded to determine if it's in the shadow. For soft shadows, we implemented percentage closer filtering by sampling a 4x4 grid around each position and averaging the shadow contribution of each offset to blur the shadow edge, and this makes the shadows look a bit more natural. We also use bump maps to add more detail into the scene, and this is done by loading a grayscale image as a height map, and then these heights are used to perturb the normal vector at each position so that the lighting reacts as if the surface is actually bumpy. We also implemented HDR, where instead of clamping illumination within 0 to 1, we rendered the full range of illumination and tone mapped it down to fit the monitor's range. And lastly, we also implemented camera movement through a predetermined path using cubic Bezier curves to traverse our scenes. And last but not least, we'll just let you traverse through our scene, so enjoy.
Oh, wait a second. There. King Kai must live on that tiny little planet. Woohoo! Check that out.
Our project is called King Kai's and is inspired by King Kai's planet from Dragon Ball Z and Super Mario Galaxy. I implemented the rigid body translation system, planet gravity, simple collision, third-person camera, camera control, and the particle system. The rigid body was a class that had the object's world space and CTM. With this information, I was able to implement simple collision by calculating the distance between primitives and setting the player's location accordingly. To implement character orientation, I got the up vector that points away from the planet, calculated the forward vector, and reconstructed a new CTM for the player's position. A similar method of getting the player's object's local forward vector is used for movement because simply moving in the X, Y, and Z directions is not good enough.
To achieve certain cartoon styles and color, I implemented the post-processing pipeline along with stylized filters and color grading. As you can see, the filters can be applied sequentially along with different lookup tables. The pipeline operates on a dedicated frame buffer, allowing effects to be layered without affecting the underlying geometry paths. The modular design makes it easy to add new stylized effects or adjust the visual tone of the scene in real time.
For our scene's geometry, we use CS1230 Scene File Creator for most of the shapes, such as the planet, house, and shed. For our character model, we use TinyOBJ's object loader to render our Goku model from Sketchfab. Our trees are procedurally generated using the turtle interpretation of L systems. We also incorporated deferred rendering into our pipeline to decouple our geometry processing from our lighting calculations, allowing for both more scene geometry and more lighting. Thank you for watching our demo.
Inspired by the human brain, the perceptron is its name. Just a weighted combination plus a threshold. Minsky and paper.
After I open my eyes, wait, I turn into a bird. It's a rainforest. And I can fly. Woohoo! I'm getting a little dizzy. Let me slow down. Oh, it's getting foggy. I feel cold. What's that? Was it always there? I swear it wasn't. What's inside? An ocean. Nope, 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 nope. Wait, come back. I don't know how to swim. Hello? Anybody here? Ah, a new door. Wow, I'm in space. Even the BGM is going strong. Okay, soundtrack, calm down. What can I do now? I might be a bird in the cartoon space forever, which is not that bad, as there is no more graphics project. Yay! I'm gonna explore the universe. Bye bye.
For our final project, what we decided to do was create a scene that cycled between 4 different seasons. The first step to doing that was actually creating the plants that live in the scene. To do that, we used L systems. These L systems are both stochastic and parametric, which essentially just means that we have more control over how the different plants look, and also that every time you load the scene, the plants look a little bit different. Using grammars, we were able to generate these plants. And the cool thing about them is that all of the plants are created using just cylinders and cones. We also used normal mapping and bump mapping to add textures.
Next is the post-processing pipeline. Instead of rendering straight to the screen, we render the full screen into an off-screen frame buffer and then composite it in a second pass. This gives us clean space to apply full screen effects like bloom and keep everything consistent. Next, we have our particle systems. This is a GPU rendered particle overlay that updates every frame and is attached to the camera so it stays spatially consistent as you move throughout. It's not just a static effect, but it's a full emitter system. Next, we have our screen space bloom. Bloom is applied to the post-process stage by extracting bright areas, blurring them, and blending that glow back over the original scene.
Another feature we implemented was God rays, which create the illusion of light scattering through the atmosphere. To achieve this, we used multi-pass rendering. First with an occlusion pass, rendering all the geometry objects as black and the light sources as white, and then applying a radial blur to those white light sources. After that, we would finally combine the scene with that occlusion texture, creating the illusion of light scattering. We also implemented instance rendering to support all these cylinders and cones that were being rendered in the scene through the L system pipeline.
Finally, we implemented shadow mapping and soft shadowing. To do this, we render a depth map from the perspective of the light, which is one directional light, the sun, in our scene. And this shows what is closer to or further from the light's perspective. Then when we render the scene as normal, we convert its position into light space and check if anything is occluding it in the depth map, which would mean it's in shadow. To do soft shadows, instead of checking one specific position, we check the position and its neighbors, about 25 positions in total, to see if anything around it is shadowed as well, and then we average those values. So instead of having a hard 0 or 1 for shadowing, we can have a continuous number there, meaning it's partially shadowed. Finally, we implemented a skybox, which is a cube positioned around the camera, textured with a cube map texture. And something interesting about the skybox is it's only transformed through rotation rather than translation as well. And this means that the camera can never actually reach the skybox, so it gives the illusion of an extremely large surrounding environment. Thank you. I hope you enjoyed.
This is Vivaldi, an animated nature environment with the ability to smoothly transition between the 4 seasons. These are the particles, instant square meshes with randomized position and velocity properties that then have a blurred circular shape from the fragment shader. They hover very nicely over this pond, which we designed by creating a noise texture which moves back and forth as a displacement map for this water texture, which creates a ripple effect. These textures are part of the multi-texture pipeline, which enables us to decorate this ground, the aforementioned lake, our seasonal post-processing, and these animals and objects. Lastly, we made an instance of an L system, a collection of cylinders algorithmically generated from a single string that rewrote itself over several iterations with the rule set to grow this tree.
In our project, we also implemented camera paths, which you've been seeing throughout this showcase. We construct a camera path through a list of keyframes, each containing time, position, and rotation. Then we calculate control points, which we can use to construct smooth Bezier curves that we move the camera along. Additionally, we implemented color grading to help create the aesthetic for the different seasons. This works by using a 3D lookup table to convert the original pixels to their new color graded ones. When we are in between seasons, we color grade using the 2 closest seasons and interpolate between them.
The project contains arbitrary meshes loaded from GLB files, including the house, trees, and animals, which are textured and in some cases animated. This was done with kinematic skeletons and linear blend skinning, which you can see in the animals' movements. There is also a skybox implemented as a cube map, which changes from interpolation between 4 different textures throughout the seasons.
Our scene also features crepuscular rays. These rays are rendered by first rendering the main scene into color and depth textures, and then doing a second pass on these textures to simulate light scattering between the camera and the light source, where every pixel traces a virtual line towards the light's position on screen. Then, along each of these lines, ray marching is done, where each sample contributes a little bit of light, and they fade as they get farther away from the pixel. And finally, to make these rays interact with the environment, a depth buffer is used as a shadow mask. Some of the textures in the scene are procedurally generated using wave function collapse. First, patterns are extracted from an input image, and then used with adjacency and frequency rules to generate a new, unique, but also similar pattern.
Hey there, I'm Albert, and have you ever wanted to make an animation but you weren't satisfied with the websites out there? Have you ever tried drawing something and thought, man, this looks like shit? Well, you're in luck. That's why I made my project, Wigglemation. So this journey actually starts off with this cool website called wigglypaint.net. It's really reminiscent of retro style animation. You've got jagged edges, random wiggles, and it reminds me of those flip note animations you could make on the DS. So let's get into it. This application builds on my first graphics project. A lot of the brushes and the logic for pixel buffers are the same, but that's pretty much where the similarities end. First off, I improved real-time responsiveness by changing my old logic. I cut down on the number of brush calls, and now I refresh the display once per mouse event. In other words, it's a lot more responsive. Secondly, I added in this cool pencil brush. It uses the constant brush mask, but adds a jitter field of tiny offsets that are randomly generated. Shout out pencils. And thirdly, I made this wiggly brush. It can wiggle. For this brush, I use 2 buffers to generate the random jitters, and a timer flips the displayed layer between the 2 buffers at some interval. I also added in a color picker and an alpha slider, as well as undo and redo functionality. If you've ever used Photoshop, you know that layers are a thing. I've also added in layer functionality so that you can turn on and off layers to keep strokes on one layer isolated from another. Alright y'all, time for the cool part, animation. So traditionally when we make animations, there's this thing called onion skinning. Pretty much when we create new frames, we can define the number of previous and next frames we want to see at a lower opacity to keep track of our strokes. It's the same as using a light table to make animations on paper. In my timeline down here, I've also added in features to duplicate frames, delete frames, and scroll through them. This was done by creating a new frame struct, wherein a single pixel buffer makes up a layer, and then I composite together multiple layers to create a frame. You can also adjust the playback speed down here, and if we play it, boom, animation. And just for your reference, this is an animation of a bear that slowly expands and then explodes and then turns into a cat. And so now you're probably wondering, this is cool and all, but what makes it different? What makes you special? Well, I can't answer that last question, but I can point you to my personal favorite feature, the wiggle mode. By modifying the amplitude, the spatial frequency, and the temporal frequency, we can create things like this. To make this, I used a 3D Perlin noise function with X and Y coordinates representing the pixel grid and the Z coordinate representing the time axis. Using a random hash and a fade function, all I did was compute the dot product of the random lattice vector with the sampling point to generate the wiggle. In other words, every frame, the 2D pixel grid is randomly being warped in a new direction. If you find yourself thinking, man, I hate my art, this might not make your art better, but hopefully it'll make you appreciate it a little bit more. After all, everyone is an artist, you just have to believe it first.
For our graphics final project, we implemented a Zen garden. This is built upon a procedurally generated grid of terrain tiles that are rakeable with the sand, which use mouse raycasting both for raking and object placement. Placeable objects were L system plants that grow along with the time of the program, and bump-mapped textured rocks to get the feeling of a Zen garden. This is all set in a skybox for the environmental feeling. and we have a controllable UI which determines which setting our mouse is on. Unfortunately, we ran out of time to fully include all of the features that we wanted to in our Zen Garden, but here's a look at some of the features that didn't quite make the cut. We had crepuscular lighting, which would have been added through clouds and other occluding factors, lending a much more atmospheric feeling to the scene. We also have depth-based fog, as well as screen blur and screen bloom, which would have been added on to interactive lanterns to be placed in the scene, contributing to a more whole feeling.
Our trees are made with L systems, which each iteration growing 5 seconds to give the effect of the tree growing, and also our rocks are made with bump mapping, where the texture is procedurally generated. And we also have flags, which are made with cloud simulations that are basically particles that are connected together through mass spring systems.
While coding your final graphics project, you forgot to convert your RGB values to floats, and now you've been banished to a sinister land devoid of color. But you're not the first. Many other devious graphics goons have been forced to walk these planes, such as Darth Shader, Jimmy Buffer, Walter Whitespace, and CPAX++. Now, it's your turn to reclaim your knowledge of the RGB color space to escape in time for final projects. But beware. There are hungry primitive cubes with the power of Z fighting after you. This is Pixel Purgatory.
Using rigid body translation with the camera, our program implements first-person gameplay. The player can jump with gravity and toggle a sprint effect to move faster. Enemies spawn from the sky in a radius around the player and drop from a distance. They are animated to bounce towards the player, and when illuminated with a flashlight, they take damage and flicker away into oblivion. The map's terrain is randomly and procedurally generated using a multi-octave noise profile. These weights influence the separation of 3 biomes, a forest filled with trees, a scorching desert, and a dark void. The goal of the game is to collect all 3 RGB color blocks spread across each of the 3 biomes, which restore their corresponding channel to the color space. Lastly, when the enemies get close to the player, they deal damage which steadily increases the static grain effect on the screen. When a player dies, a ghost of them will follow their recent footsteps and glide towards the player's old position using camera paths.
Trees and ground surfaces are textured using bump and normal mapping, which vary per biome. To create the illusion of death, normal mapping uses RGB color to store the X, Y, and Z vector direction, while bump mapping uses grayscale height data.
Fog exists in all biomes, however its color changes depending on the region. Its visibility and closeness to the player improves with the use of the flashlight, which relies on a power meter and flickers off when the energy is depleted. Sound effects accompany the player's footsteps, flashlight toggling, enemy movement, enemy death, and other general ambient noise.
Instance rendering is used to track particle effects, which include dirt particles that follow you while walking, fading wisps in the void biome, and dust particles that rise from the ground. In the post-processing pipeline, we include a warm color grade, texture pixelization, and some stylized filters like a static grain and vignette to achieve a more haunting and retro look, with the color being changed per achievement. We also include a screen space bloom to add a glow to bright light sources, and motion blur to blend camera movement.